Trigonometry, Chapter 5, Trigonometric Identities, Section 4, More Identities, Video 9, Power Reducing Identities. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous videos, we derived and used sum-to-product identities. Here you see a list of all four of them. It's worth reminding you that I have none of these memorized, but I know how to derive all of them. If I need them during a problem, I can either rederive them or look them up. In this video, we derive and use the power-reducing identities. Specifically, we will derive identities for cosine squared x and sine squared x. We start by observing two of the three double angle identities for cosine. Notice that these identities contain cosine squared and sine squared. Cosine 2x equals 2 cosine squared x minus 1, and cosine 2x equals 1 minus 2 sine squared x. Solving each of these for their squared trig functions only requires basic algebra. We're going to move the ones from the right sides to the left side, so each one will change signs as we move it to the left side. So we get 1 plus cosine 2x equals 2 cosine squared x, and negative 1 plus cosine 2x equals negative 2 sine squared x. Again, just moving the ones from the right side of these double angle cosine identities to the left side. Next, we're going to multiply both sides by the reciprocal of the squared trig functions. For example, we're going to multiply both sides of the top equation by 1/2 and both sides of the bottom equation by negative 1/2. That will isolate the squared trig functions on both. Now, for a little cleanup on the second one, we're going to take the negative off this 1/2 and distribute it to the two terms in the parentheses, making the 1 positive and the cosine 2x negative. And notice that the left sides of these pretty much have identical structure except one is plus and one is minus. And these are our power-reducing identities. Notice that the power on the trig function is reduced by a factor of 2. For example, we have cosine squared x on the left, and on the right we have 1/2 times 1 plus cosine 2x. So the power gets reduced from 2 to 1 in exchange for the argument of the function being doubled. The argument of cosine squared x is x. The argument of cosine 2x is 2x. So power gets reduced by half, and the argument gets doubled. Same thing for sine squared of x equals 1/2 times 1 minus cosine of 2x. In calculus, it's much easier to perform operations on trig functions with no powers, in other words, powers of 1, than with powers greater than 1. So this is commonly used in calculus to make trigonometric expressions manageable. Here's an example of using a power-reducing identity to totally eliminate a power on a trig function. For example, we're going to rewrite cosine to the fourth power of x, or cosine x, the fourth power of cosine x, with no powers. Now, notice that this is not a square, but it's an even power, which means it's twice an even number. So we're going to rewrite cosine to the fourth power of x as cosine squared of x squared, just like we did here. Now, that exposes the cosine squared of x, which we can replace with its power-reducing identity, 1/2 times 1 plus cosine 2x. So the cosine squared x will become 1/2 times 1 plus cosine 2x, like that. At this point, we have a little bit of algebra to do. We're going to square the 1/2, which will make it a 1/4, but we're also going to square the 1 plus cosine 2x by doing a FOIL problem, 1 plus cosine 2x times 1 plus cosine 2x. If we do all that carefully, we'll get 1/4 from squaring the half, and 1 plus 2 cosine 2x plus cosine squared 2x by squaring the 1 plus cosine 2x. Well, not too bad, but we still have a power here on this last term, power of 2. Well, we know what to do with that now. We have another squared cosine, but this time the argument is 2x. So we're going to apply the power-reducing identity again. And remember, the argument will double, so it will double from 2x to 4x, and the power gets halved. So if we replace the part on the inside with what we get when we apply the power-reducing identity for cosine squared, We're going to replace that with 1/2 times 1 plus cosine of 4x. Again, the argument doubles when you apply the power reducing identity. And so now we have 1/4 times 1 plus 2 cosine 2x plus all this that we brought in for the cosine squared 2x, specifically 1/2 times 1 plus cosine 4x. Now let's clean it up. Let's distribute the 1/2, giving us 1/2 plus 1/2 cosine of 4x. And now we have constant terms of 1 and positive 1/2 to combine. 1 plus 1/2 is 3/2. And while we're at it, we might as well just distribute the 1/4, giving us the final result of 3/8 from 1/4 times 3/2, plus 1/4 of 2 cosine 2x, which is 1/2 cosine 2x, plus 1/4 times 1/2 cosine 4x, which is 1/8 cosine 4x. No more powers. So doing calculus, believe it or not, is much easier on this expression than cosine to the 4th power of x. So our answer is cosine to the 4th power of x equals 3/8 plus 1/2 cosine of 2x plus 1/8 cosine of 4x. Now you try. Pause the video and try the following. Write sine to the 4th power of x with no powers. All right, if you haven't paused the video and tried, here's your fair warning. Solution in 3, 2, and 1. We pretty much take the same course. Rewrite sine to the 4th power of x as sine squared of x squared, but then replace sine squared of x with its half angle identity, 1/2 times 1 minus cosine 2x. And then if we square that, it's going to look almost exactly like we were before. In fact, this part over here, the 1/4 times 1 minus 2 cosine 2x plus cosine squared 2x, is exactly what we had here, except the minus in the middle. So since the only difference is the minus in the middle, our answer should essentially be the same. And it is. Sine to the 4th power of x equals 3/8 minus 1/2 cosine 2x plus 1/8 cosine of 4x.